If you were asked to think of 3 renewable energy sources, the sources that would likely come to mind are solar energy, hydroelectric energy, wind energy, or any sources of energy that are present in nature. But what if there's a source of energy that comes from mankind, a source of energy that can be found within cities or even the comfort of your own home, a source called sound? The idea of harvesting energy from sound is uncommon and consequently overlooked, but that is not how it should be. With a rapid increase in vehicles and indoor entertainment centers, sound pollution has reached a point where in 2025, it is estimated that over 1 billion people experience unhealthy levels of it. The source of this energy is currently being wasted, hence the need of a solution. My name is Namie Djaja from Sekolah Ciputra, Surabaya, and I am here with my partner, Kaylee and Siswanto from Cita, Hati Christian School. Today, we bring forth our study, the prototype design and analysis of piezoelectric sound-to-energy conversions in high-noise indoor spaces. In this study, we aim to explore the idea of acoustic energy in indoor spaces, primarily movie theaters as they are high-noise enclosed environments, and to create a device to harvest the energy without disrupting the existing functions of the indoor space. As the study progresses, we aim to answer the question of how to optimize the potential difference output of the device in these spaces. Now, to create the device, we intend to make use of the properties of piezoelectric materials. What exactly are they? Well, piezoelectric materials are materials that have a property that when put under mechanical stress, a voltage is produced. Piezoelectric materials were initially discovered in the 19th century and have made their debut in World War I for sonar imagery. Since then, they have been used in medical application, precision engineering, sensors, and much more. However, despite its wide application sets, piezoelectric materials are not used in indoor sound energy harvesting, as it is more popularly used to harvest kinetic energy. Thus, our proposal.
Here is the protocol diagram or the wiring diagram for a piezoelectric generator. Here are the materials and tools needed to assemble the piezoelectric generator. So this slide shows the physical prototype. On the left, you can see our initial setup with only one piezoelectric generator connected to the breadboard. This was done to test the basic functionality and to check if the piezo could convert sound vibrations into measurable electrical signals. While on the right, we expanded the system by connecting multiple piezoelectric generators on the breadboard. This increases the surface area for the vibration capture and allows more energy to be generated from the sound waves. Here are the expectations for the piezoelectric discs. With 5 discs, only small voltage spikes are expected, with moderate levels of sensitivity. With 10 discs, a higher total voltage or more consistent signal output is anticipated due to the increased number of active surfaces, while with 15 to 25 discs, greater overall energy output and improved signal averaging are expected, resulting in more stable and reliable performance. So in general, as the number of discs are increased, both the voltage output and the signal stability are expected to improve.
Moving on to the actual data collection and processing, we aim to answer our research question of how to optimize the potential difference output measured in millivolts by measuring the effect of changing the frequency of the sound waves as well as the number of piezoelectric transducers used. The tests will be conducted on a range of different frequencies measured in hertz that are commonly present in movie theaters, namely 4,000, 6,000, 8,000, and 10,000 hertz. Alongside this, the tests will also be conducted on 5 different amounts of piezoelectric transducers used: 1, 5, 10, 15, 20, and 25. These are the raw data results that we have gotten. To process the data, we have plotted 4 different kinds of scatter graphs: logarithmic, polynomial, exponential, and linear. And through a comparison table of the points the gradients have passed through, it is clear that the polynomial graph is the most accurate as it passes through all of the points plotted correctly. With this information, we can now use the polynomial graph to predict the potential difference outcome of using 30 or more piezoelectric transducers. Now, taking a closer look at the raw data results, we have observed 2 clear trends. The trend that the number of piezoelectric transducers is directly proportional to the potential difference output, and the trend that the frequency of sound waves is inversely proportional to the potential difference output. We deduced that the explanation behind the first trend is as each piezoelectric transducer experiences the same mechanical stress and produces the same output, Increasing the amount of producers of potential difference will increase the total potential difference outputted. As for the second trend, we believe that it can be explained through the equation C equals lambda times F, where C represents the speed of the wave, F represents the wave's frequency, and lambda represents the wavelength. Since the medium the sound travels into is kept constant, the speed should be constant. Consequently, we can apply the idea that the wavelength is inversely proportional to the frequency. As a sound's wave strength is dependent on its amplitude or wavelength, increasing the frequency would decrease its wavelength and the potential difference outputted.
This figure shows the proposed prototype for the piezoelectric sound energy harvesters applied in a movie theater. The setup positions piezoelectric generators near the front of the speakers supported by metal bars so that the sound vibrations can be captured efficiently. These vibrations are then transferred into the mounted piezoelectric generators, which convert the acoustic energy into electrical signals. The placement in front of the speakers was chosen to maximize vibration exposure while maintaining practicality while integrating it into a theater environment. This prototype demonstrates how sound, which is normally considered as noise pollution, can be repurposed into a useful energy source. In conclusion, our prototype successfully demonstrated that piezoelectric discs can convert sound vibrations into measurable electrical energy. Although the energy produced is small, it is sufficient to power low-power devices. This validates the feasibility of the concept and shows promise for applications in sound-rich environments. However, there were several limitations. Variations in sound intensity led to fluctuations in the output. The multimeter was limited in precision, which likely caused the underestimation of short voltage spikes. Additionally, small energy losses occurred, likely due to the resistance in the wires. Finally, inconsistent mechanical contact between the sound source and the piezo elements reduced the efficiency. To overcome these issues, improvements can be made. A wider range of piezo quantities tested in smaller increments would provide more detailed insights. Expanding frequency testing to include lower ranges would also give a more comprehensive analysis. Furthermore, using a more stable and a uniform mounting system would ensure consistent vibration transfer and reduce the energy loss. Here are the references. The sound that distracts us today could be the energy that powers our tomorrow. Thank you.